Today we're going to explore a bit of capacitor theory, and a capacitor is a device for storing charge, and because it stores charge it also stores energy, and put simply it consists of just two metal plates that are parallel like this, and if you connect them up to a battery, then this long one is the positive one, and so if this is positive, what you get is a whole lot of positive charges build up on this plate, and simultaneously you get a whole lot of negative charges, in fact the same number of negative charges building up on this plate. Of course, like charges repel, but they're held there by the supply voltage. If, however, we then connect this capacitor to a light bulb, then those like charges will repel and they'll all come off the capacitor and dump their energy in the light bulb. So that's how a capacitor is able to store both charge and energy. And the remarkable thing, it's remarkable to me anyway, about a capacitor is that we can define its capacitance very simply. If we do an experiment where we say, well, okay, what happens when we increase the voltage across the plates? We find that actually you get a dead straight line. And because it's a straight line, then that means that V is proportional to Q. And in practice, we define the capacitance such that it's written this way round. The charge is the capacitance times the voltage. So that tells us that capacitance has units. Units. Let me see. You can tell me what the units. The capacitance is in coulombs per volt. But actually, capacitors are sufficiently important that they have their own unit, and it's called the farad. Symbol or abbreviation capital F. So there you have it for capacitors. In a nutshell, what could be simpler? Another remarkable bit of physics whereby a straight line through the origin is the answer. Q is proportional to V, and so we can define the capacitance as being the ratio of Q to V, but it's Q equals CV, not V equals CQ. So what does that mean? Well, what that means is that the greater the capacitance, the more charge you get per volt. So it's kind of like the capacity to store charge. So it sort of makes sense, just in the same way as resistance is the kind of reluctance of a metal to conduct current when a voltage is across it. So R equals V over I, not I over V. Of course, there is something called conductance, which is I over V, which is 1 over the resistance. So we could define this either way, but the capacitance is the ratio of Q to V and is measured in coulombs per volt. Now, if we want to make a bigger capacitor, then what we can do is we can put the plates closer together, or we can make the plates bigger. Unfortunately, however hard we try, however, generally speaking, capacitors made this way are microfarads at best. Turns out the farad is a large unit for most easily accessible operations, if so to speak, and therefore we usually talk about microfarads or even nanofarads, even picofarads. So you don't often find a 1 farad capacitor. Okay, so that's part 1, and so I'll write part 1 up here, and then we get on to part 2. Part 2 concerns Kirchhoff's first and second laws. Go away. I've written K because I don't know how to spell Kirchhoff, and it's embarrassing. So Kirchhoff's first and second laws, hopefully you remember that the first law is the current rule and the second law is the voltage rule. And the thing that's perhaps surprising is that both these rules still apply. So what I mean by that is that, coming back to the picture that we had, a little circuit that I drew up here, if you've got a current here where the conventional current is going onto the plus plate, then you must have a current here too. And those two currents are not only equal, but they're equal at all times. One of the factors that's more complicated with capacitors is that you don't often get steady state current. The capacitor is either charging up or it's discharging. If it's charging up, then as it gets more and more charged, it charges slower and slower. As it's discharging, well, initially the discharging current might be quite high, but then the discharging current changes or reduces. But at every instant in time, the current from one plate must be equal to the current on the other plate. So even though the current doesn't actually pass, the charges don't pass through the capacitor, Kirchhoff's first law still applies, and what's more, at all times, at every instant in time. What about Kirchhoff's second law? Well, if you've got a resistor in series with a capacitor, then the voltage across the resistor plus the voltage across the capacitor must equal the voltage of the supply. So that's Kirchhoff's second law, the voltage rule. So we can use these two ideas to look at series and parallel arrangements of capacitors. So this is the last thing I'm going to do in this particular talk. Series and parallel capacitors. If you've explored already the FET from Colorado University, you may have looked at series and parallel capacitors already. But let's just see what I can add to that. Series and parallel capacitors. Here we are with our supply, and we're going to put a couple of capacitors in series, like this. Here they are. They may not be the same capacitance, so we better call this one C1 and this one C2. But I've already said that Kirchhoff's first law applies. So at every instant in time, the current here is the current here is the current here and here and here. So therefore we can say that Q1 equals Q2, so I'll just call it Q, equals the integral of I dt, because there is only one current, and current is the rate of flow of charge, so charge is the integral of I dt, and so we've got charge on this one and charge on that one. Fine. Okay, well, what does that mean? Well, let's change to green. There's going to be V1 across C1 and V2 across C2. And what we know is Kirchhoff's second law tells us that V0 equals V1 plus V2. Okay, but we've got, so I better put a but. The formula for capacitors is that in general, Q equals CV. I'll put a box around that because there's no particular Q that I'm talking about. That's just the formula. And so looking at C1 V1, this is going to be equal to C1 V1, and this is also going to be equal to C2 V2 because the charges are the same. And the total charge stored is Q. So looking at this, we can then say, therefore, V0, which is Q0 over C0, equals V1, which is Q over C1, plus V2, which is Q over C2. And clearly the Q's cancel. So really what I've done is I've just gone from V0 equals V1 plus V2. V0 is Q over C0. V1 is Q over C1. V2 is Q over C2. So because I can, I'm just going to scrub those Q's out. And right. This is very reminiscent of the resistors in parallel rule, but this is capacitors in series. And so as a result, we've connected them in series, and we've actually got a lower combined capacitance. So if you want to make a really big capacitor, don't connect them in series. You're just going to get a smaller and smaller capacitor. So what about parallel? Okay, well, we better have a parallel circuit next. Whoops, I'm not going to be using that line. I need to remember to put the battery in. Okay, here we are. And we're going to have one capacitor here. And one capacitor here. And this time, the thing that's the same for the two capacitors is the voltage across them. V0, V0, V0. And then this one's C1, and this one's C2. And we know that from Kirchhoff's first law that the current that comes along here, I think I was using red for current, wasn't I? Why not stick with it? Let's go for current along here, but this current will be I1 and this current will be I2, and the two currents will add up to I0. So in this case, we will get Q1 over C1, and we'll get Q2 over C2. So therefore, the combined capacitance, the thing that's the same now for these capacitors is the voltage. So we can say that the total charge stored, which is Q0, equals Q1 plus Q2. And Q equals C times V, so this is C times V0. And Q1 is C1 times V1, but V1 is the same as V0 because there only is one voltage. And Q2 is C2 times V0. So finally we see, and I think I should be in green pen really, we get C0, which is the combined resistance, capacitance, sorry, is C1 plus C2. So if you want to add capacitors to make a bigger capacitor, put them in parallel. This is parallel. And this one is series. Okay, so that's it for now. So what I suggest you do, if you haven't done it already, is go and have a look at the FET applet and fiddle around. You can make circuits that are in series and in parallel and see how much each charges. See if it confirms these formulae. Hopefully it will.